So, what is the ideal angle of attack for a wing? Is it the sort of critical angle of attack, or just before the critical angle of attack where we get the maximum lift coefficient? So, right before stall, where lift is a maximum. Well, what we also need to think about is our drag coefficient. And you can see here, we've talked about this before, that as we increase the angle of attack, we'll also get an increase in the drag coefficient. And that is due to partly due to parasite drag, an increase in the sort of form drag, and an increase in lift induced drag as well. So it's not that straightforward. We have to think about the lift coefficient and the drag coefficient and sort of strike a balance between the two. So what we can look at is our lift to drag ratio, essentially our ratio of the lift coefficient to the drag coefficient. And that's a bit more sort of useful than just looking at the lift coefficient. So we can see that if we plot the lift to drag ratio against the angle of attack, um, and we do get this point where we get an optimum, a maximum lift to drag ratio. And that typically happens if we come down here, somewhere between sort of 3 and 4 degrees angle of attack. So you often find that the aircraft will cruise at sort of 3-4 degrees angle of attack. So you've seen this lift formula and this drag formula before, where we've got our lift coefficient and we've got our total drag coefficient. And we've sort of used those formulas independently, but now we actually have a link, I guess, between them through the drag polar. So we can now sort of essentially deal with them both at the same time for a given problem. So the related CD and CL are, as I said before, related through the drag polar, and CD naught in this case is our zero lift drag coefficient. So that is partly made up of the zero lift parasite drag coefficient and the zero lift wave drag coefficient if we do have any shock waves. And then our K value is found using these sort of constant values. So K1 is dependent on the change or the increment in parasite drag when we're generating lift, and K2 is the change in wave drag when we're generating lift. So the lift to drag ratio um, is sometimes called the glide ratio or the aerodynamic efficiency. I will use sort of all three of those expressions depending on the sort of context. So just be aware that all three of those essentially mean the same thing, the lift to drag ratio or the ratio of the lift coefficient to the drag coefficient. So you can see a range of lift to drag ratios here on the right hand side in this table. These are approximate lift to drag ratios, but you can see the sort of range that we're talking about. So for the B52G, which is pictured here, you can see there's quite a high lift to drag ratio of 20.5. You should be thinking, well, why is that? What is the reason for that? And it's because the B52G is a long range aircraft. So the higher the longer the range that we want, then the higher the lift to drag ratio. So yeah, the B52 is a sort of long range bomber, whereas the XB70A sort of down in this region is more of a short range bomber. So it depends on what we're after for our aircraft. Some very high performance gliders can operate with very large aspect ratios, sort of very long and thin wings, and basically we'll talk about wing design as we move forward, but that leads to essentially a very large glide ratio. and that can be in excess of 25 for some gliders, and that essentially means that they have a very long range.